In this question, we're given a reaction, and we are given the Kp for this reaction as 2.3. And then we're given several conditions, A, B, and C, that we would find this reaction under. So, Kp for this one is equal to products over reactants. So since it's Kp, it's pressures. The pressure of N2 times the pressure of H2O squared, because there's two of them, divided by the reactants, the pressure of NO squared, because there's two of them, the pressure of hydrogen squared again, because there's two of them. So we have two NOs and two hydrogens. So this is the expression for Kp. We now need to introduce a new expression that looks almost exactly the same, which is Q. Q equals the pressure of N2, pressure of water squared, divided by the pressure of NO squared, pressure of H2 squared. Mathematically, the equations look the same. However, the difference is that Kp is the equilibrium constant, so it's at equilibrium. Q is at any set of conditions. And here we have a set of conditions which may or may not be at equilibrium. It may be at equilibrium, but it may not be. So there are three possibilities that could happen. Q could be greater than Kp, meaning the value of Q is greater than the value of Kp. For Q to be greater, it means the pressure of the products the pressure of the products must be greater, and or the pressure of the reactants must be lower than at equilibrium. Because to make this number larger than this number, you either have to have a bigger number on the top and or a smaller number on the bottom. That will make Q bigger. So if Q is greater than Kp, we need to get rid of some of the products and or gain more reactants. In order to get rid of products or gain more reactants, the reaction has to shift left towards the reactants. That'll give us more reactants and less products. So if Q is greater than Kp, to get back to equilibrium, we'll shift in this direction. Q could of course be less than Kp. In this case, that means that this number is smaller than this number, which means you either have more of the reactants and or less of the products. So you need less reactants and more products. The reaction shifts in the forward direction. Or Q could be equal to Kp, which just means that the reaction is at equilibrium. So here, the reaction's already at equilibrium. I'm just going to put it as an equal sign because that's all that'll fit. So this is basically the case. So now we just need to plug in these numbers and figure out how Q relates to Kp, and Kp is given as 2.3 in the problem. So in the first case, we have Q equals the pressure of nitrogen, which is 9, times the pressure of water, which is 7.74. We want to square that, divided by the pressure of NO, 2.36. We want to square that, and the pressure of hydrogen, which is 6.47, and we want to square that as well. So we're just plugging into this equation. When you do that, you find that Q equals 2.3. Well, Q and Kp are exactly equal. That means the reaction is at equilibrium, so the reaction is not going to shift, and you will have no change in any of these concentrations. I'm going to skip B because in this case it's also no change, and I'm going to skip down to C, which you do exactly the same way. Q equals, in this case, the 9.49, which is the pressure of nitrogen, times, in this case, the pressure of water is 8.72, square it, divided by the pressure of NO, the first reactant, is 1.38. There are two of them, so we square it. Times, there's two hydrogens, so we put 5.49 on the bottom. And again, since there's two of them, we square it. In this case, the value of Q is 13. Note that this is case C, not case B. So, Q is 13, Kp is 2.3. So Q is greater than Kp. This is 13, this is 2.3. So Q is greater than KP. Well, if Q is greater, that means we either have more products that we need or we have less reactants that we need. Of course, both are possible. So in this case, or both are true, so in this case, we need the reaction to get rid of some of the products and make more of the reactants. In order for that to occur, the reaction has to shift to the left towards the reactants. Well, if the reaction shifts left towards the reactants, I'm going to increase the amount of each reactant that I have because the reaction will shift left. And then I will also, because I have to make those reactants from something, I will make those reactants from the products because I'm shifting in the reverse direction, so I will decrease the amount of each of the products. So that is how you would solve this problem, and you could do the exact same thing for letter B as I mentioned before.